What if everything you see, every star, every galaxy, even the very fabric of space itself, has a perfect doppelganger lurking just beyond our perception? Picture a cosmic mirror, reflecting not just light but reality itself, creating a twin universe identical to ours in every way, yet forever out of reach. This isn't the plot of a sci-fi blockbuster, it's a groundbreaking theory that's shaking the foundations of modern cosmology. Welcome to Two Universes, One Origin Story, cracking the mirror of cosmic evolution, where we'll venture into the mind-bending possibility that our universe might not be alone. In fact, it might have a mirror image born from the same explosive moment of creation, a hidden twin echoing our existence in ways we're only beginning to understand. Think about the Big Bang, the violent birth of everything we know. But what if that moment didn't just create one universe, but two? Like a seed splitting into identical halves, the cosmos might have unfolded in perfect symmetry, giving rise to parallel realities that mirror each other down to the smallest particle. It's an idea that blurs the line between science and philosophy, forcing us to ask, could the answers to our deepest cosmic questions, dark matter, quantum weirdness, even the nature of time itself, be hiding in that mirrored realm? The implications are staggering. If true, it would mean we're living in just one half of a grander, more mysterious whole. This is where the journey gets thrilling. From the bizarre behavior of entangled particles spookily connected across vast distances to the enigmatic shadows of distant galaxies that shouldn't exist, the clues are piling up. Scientists are now peering into the cosmic mirror, searching for cracks that might reveal our universe's hidden twin, and what they're finding could rewrite the story of everything. So if you've ever stared at the night sky and wondered what lies beyond the edges of our reality, you're in the right place. Together, we'll unravel these mysteries piece by piece and explore what it truly means to live in a universe that might have a reflection staring back. The Big Bang is often described as the ultimate beginning, a single, cataclysmic explosion that birthed our entire universe. But what if that moment wasn't just a solo act? Imagine the universe's birth not as a solitary event, but as a cosmic pair of twins emerging together in perfect symmetry. This isn't just speculation, it's a theory gaining serious traction among physicists, rooted in the elegant mathematics that govern our reality. Quantum symmetry, the idea that nature prefers balance at the deepest levels, hints that our universe might not be complete without its mirrored counterpart. Think of it like a coin toss at the dawn of time. Heads, our universe bursts into existence. Tails, its twin emerges in the same instant, identical yet inverted. This mirror universe wouldn't just be a vague reflection. It could share the same fundamental particles, the same physical laws, even the same galaxies and stars, but with subtle, critical differences. One intriguing possibility, dark matter, the invisible glue holding galaxies together, might actually be ordinary matter from this mirrored realm, leaking into our universe like whispers through a cosmic wall. The evidence for this duality isn't just theoretical. Scientists studying the cosmic microwave background, the faint afterglow of the Big Bang, have spotted anomalies that defy conventional explanations. Tiny temperature fluctuations, odd patterns in the distribution of matter, these could be cosmic fingerprints left by our universe's hidden twin. Even particle physics adds weight to the idea. Neutrinos, those ghostly particles that barely interact with matter, seem to oscillate in ways that suggest they might be flickering between our universe and its mirror. But here's where it gets truly mind-bending. If this mirrored universe exists, time itself might flow differently there. What if the arrow of time points backward in that realm, making its history our future and vice versa? Or what if the two universes are entangled, their fates forever linked across an unfathomable divide? These questions aren't just philosophical, they could reshape our understanding of reality. The search for this cosmic twin isn't just about solving puzzles, it's about rewriting the story of existence. Every discovery, from the behavior of subatomic particles to the large-scale structure of the cosmos, brings us closer to answering one of science's ultimate questions. Are we truly alone in the universe, or is there another version of everything, silently echoing our every move? Quantum entanglement is one of the strangest and most baffling phenomena in physics. Two particles, no matter how far apart, somehow remain mysteriously linked, instantly mirroring each other's states. Einstein famously called it spooky action at a distance because it defies everything we know about space and time. But what if this quantum weirdness isn't just a quirk of our universe? What if it's actually a cosmic handshake, an invisible thread connecting our reality to its mirrored twin? Imagine two particles entangled at the birth of the universe. In our world, one spins up and instantly, its counterpart in the mirror universe spins down, perfectly balanced like seesaws across the divide. This isn't just speculation. Some physicists argue that entanglement might not be a random quantum fluke, but a fundamental feature of a deeper, dualistic cosmos. If particles in our universe can sync with their twins in another, it would mean the two realms are woven together in ways we're only beginning to grasp. Think of it like a cosmic game of telephone, where the message isn't traveling through space, it's bypassing it entirely, as if the two universes share a hidden back channel. This could explain why quantum mechanics feels so bizarre compared to the predictable laws of classical physics. The rules aren't broken, they're just operating on a scale far grander than we realized, with every particle's behavior influenced by its unseen twin. The implications are mind-blowing. If entanglement bridges universes, then every time scientists measure a quantum particle state, they might unknowingly be glimpsing the shadow of its mirror counterpart. It's like tuning a radio and catching whispers from a parallel station, faint, distorted, but undeniably there. Some researchers even suggest that dark matter, the elusive substance making up most of the universe's mass, could be ordinary matter from the mirror realm, leaking into ours through these quantum backdoors. But here's the real kicker. If entanglement ties the two universes together, it might not just be particles that are linked. Entire galaxies, stars, even versions of ourselves could have mirrored counterparts, forever synced in ways we can't yet perceive. The cosmic web we see, the vast structure of galaxies stretching across the void, might be just one half of a grander tapestry, its threads extending into the unseen. Of course, proving this isn't easy. How do you detect a universe you can't see? Scientists are hunting for subtle anomalies, tiny deviations in quantum behavior, unexplained ripples in gravitational waves, even strange echoes in the cosmic microwave background. Every experiment probing the quantum realm could be a step toward cracking the mirror's code. And if they succeed, it wouldn't just solve the mystery of entanglement. It would rewrite our place in the cosmos, revealing that we've never been alone in the universe. We've just been looking at half the picture. Dark matter has long been the cosmic puzzle piece that refuses to fit. We know it's there, galaxies spin faster than they should, light bends around invisible mass, and the universe's structure hints at something massive lurking in the shadows. Yet despite decades of searching, we've never directly detected it. What if the reason is simpler and stranger than we ever imagined? What if dark matter isn't some exotic particle in our universe at all, but ordinary matter from another? Enter the mirror universe hypothesis. Picture this: every proton, every electron in our cosmos has a twin in a parallel reality, identical in every way except one: they only interact with our world through gravity. That means while stars and planets in the mirror universe would tug on ours just like dark matter does, they'd remain completely invisible to our telescopes and particle detectors. It's like living next to a house with glass walls. You can't see the furniture inside, but if someone pushes a couch against the shared wall, you'd feel the pressure. This idea flips dark matter from a missing ingredient into a cosmic neighbor. Suddenly, the math starts to click: the amount of dark matter we've calculated. It lines up eerily well with the estimated mass of visible matter in our universe, and those unexplained gravitational ripples in galaxy clusters. They could be the fingerprint of entire mirror galaxies overlapping with ours, their mass warping space-time from the other side of reality's veil. But here's where it gets truly fascinating. If dark matter is just mirror matter, it solves another head-scratcher: why we've never caught it in underground detectors. Experiments like those in deep mines, shielded from cosmic noise, have spent years hunting for dark matter particles colliding with ordinary atoms. But if dark matter exists in a parallel universe, it wouldn't bump into ours at all. It'd glide right through, leaving no trace except gravity's gentle pull. The implications ripple outward. Imagine two universes born from the same Big Bang, their histories perfectly mirrored. A supernova in ours might have an identical twin exploding unseen in the other. Civilizations could rise and fall in that shadow realm, never knowing we're here, while their gravity shapes the cosmos we call home. It's a humbling thought that the missing 85% of the universe's mass might not be missing at all. It's just been next door this whole time, hidden behind the ultimate cosmic curtain. Scientists are already devising ways to test this wild idea. Some are studying neutron stars' ultra-dense stellar corpses for subtle gravitational anomalies that could hint at mirror matter's presence. Others are re-examining the cosmic microwave background for asymmetries that might reveal a twin universe's faint imprint. If even one of these searches pans out, it wouldn't just solve the dark matter mystery. It would redefine our place in the multiverse, proving we've never been alone in the grand scheme of things. At the heart of modern physics lies a deceptively simple idea that the universe might look exactly the same if you flipped it inside out, reversed the flow of time, and swapped every particle for its opposite. This is CPT symmetry, a fundamental rule suggesting our reality could be perfectly balanced by an inverted twin. Charge, parity, and time, three seemingly separate concepts intertwined to form a cosmic mirror, reflecting a universe where stars are made of antimatter, galaxies spin backward, and time itself runs in reverse. Take a single electron, for example. Its mirror counterpart would have a positive charge, an antimatter twin called a positron. Flip its spatial orientation like a glove turned inside out, then rewind its timeline like a film played backward. According to CPT symmetry, this transformed particle should behave exactly like the original. Now, scale that up. Imagine every atom, every planet, every black hole undergoing the same inversion. The result, a universe that's not just similar to ours, but mathematically identical, just viewed through a funhouse mirror of physics. Some theorists take this even further. If CPT symmetry holds universally, it might not just describe hypothetical transformations. It could imply a real, physical mirror universe coexisting with ours. Picture two cosmic DVDs playing simultaneously, one forward, one in reverse, each perfectly encoding the other's story. In this mirrored realm, the Big Bang might appear as the Big Crunch, with time flowing toward an infinitely dense past instead of an expanding future. Supernovas there could explode backward, reassembling stars like celestial puzzle pieces. Even life, if it exists, would experience reality in reverse, with trees absorbing carbon dioxide and sunlight to decompose into seeds. The implications ripple across every mystery in physics. Why is our universe made almost entirely of matter, with antimatter vanishingly rare? CPT symmetry suggests an elegant answer: the missing antimatter didn't disappear. It's all around us, just locked in the mirror universe, invisible but gravitationally present. This could explain dark matter's elusive nature, as antimatter galaxies in the twin realm would tug on ours without ever colliding. Even the arrow of time, that relentless march from order to disorder, might be a local quirk, an illusion created by our one-sided perspective in a two-sided cosmos. Testing this isn't just theoretical. Particle colliders like the Large Hadron Collider are already probing the edges of CPT symmetry, hunting for tiny violations in the behavior of particles and antiparticles. Astronomers, too, are scanning the cosmic microwave background for anomalies, subtle temperature variations, or polarization patterns that could betray the mirror universe's gravitational whispers. A single crack in CPT symmetry's perfect mirror could rewrite cosmology, proving we've been sharing existence with an inverted twin all along. Yet the most profound question remains: if this mirrored cosmos exists, could we ever communicate with it? Quantum entanglement hints at a possible bridge: particles instantaneously linked across unimaginable divides. Perhaps the same phenomenon binding electrons across light years could thread the needle between universes. One thing's certain: unlocking CPT symmetry's secrets wouldn't just reveal a hidden twin universe. It would force us to redefine reality itself, showing that the cosmos has always been twice as strange and twice as beautiful as we ever dreamed. What if time isn't a one-way street in the cosmos, but a two-lane highway where events in the mirror universe flow in the opposite direction? Picture a pair of cosmic dancers, perfectly synchronized yet moving in reverse. Every step we take forward, our mirrored twin takes backward. This isn't just poetic symmetry, it's a radical rethinking of cause and effect. If the mirror universe runs backward in time, the consequences ripple far beyond theoretical physics, challenging our most basic assumptions about reality. Take a supernova explosion in our universe, a star's violent death sending shockwaves through space. In the mirror realm, that same event might unfold in reverse: scattered stardust collapsing inward, reassembling into a blazing sun. From our perspective, it would look like time rewinding, but for the mirror universe, it's just the natural flow of events. Even more mind-bending: what if these twin phenomena are entangled? A black hole forming here could trigger the unforming of one there, as if cosmic destruction in our world fuels creation in the other. This flipped timeline isn't just about spectacle. It could solve one of physics' biggest puzzles: the arrow of time. Why does time move forward at all? The second law of thermodynamics tells us entropy, or disorder, always increases, giving time its direction. But if entropy decreases in the mirror universe, the two realms could balance each other out like cosmic bookends. The total entropy of the multiverse might remain constant, with our universe's chaos offset by the mirror's growing order. Now, imagine the implications for causality. If events in the mirror universe influence ours retroactively, the future could be shaping the past. A star's birth today might depend on its mirrored counterpart's death billions of years from now. It's a loop where cause and effect aren't just blurred, they're intertwined like strands of a Möbius strip. Some physicists speculate this could explain quantum weirdness, like particles seeming to know their future states. Maybe they're not clairvoyant, just entangled with their time-flipped twins. The real test, looking for evidence in the fabric of space itself. Gravitational waves, the ripples from colliding black holes, might carry echoes of mirror universe events. If scientists detect waves with inverted properties like spins going the wrong way, it could be a smoking gun. Even the mysterious cold spot in the cosmic microwave background, a patch of space suspiciously emptier than it should be, might be a window into the mirror realm's gravitational tug. But here's the kicker: if time flows backward there, does that mean the mirror universe remembers our future? Could its history books already contain events we haven't experienced yet? The answer might lie in quantum entanglement's spooky connection, threading through time as effortlessly as space. One thing's certain: if this mirror timeline exists, the universe isn't just stranger than we imagined, it's stranger than we can imagine. A cosmic hall of mirrors where every step forward is also a step back. Our universe has a glaring asymmetry, one that's puzzled physicists for generations. During the Big Bang, matter and antimatter should have been created in perfect, equal amounts, annihilating each other in a flash of energy and leaving behind nothing. Yet here we are, surrounded by galaxies, stars, and planets made entirely of matter. So where did all the antimatter go? The answer might not lie in some forgotten corner of our cosmos, but in an entirely separate reality, a mirror universe where antimatter didn't just survive but thrived. Think of it like a cosmic seesaw. At the moment of creation, the universe could have split into two perfectly balanced halves, one tilting toward matter, the other toward antimatter. In our world, protons carry a positive charge, electrons are negative, and atoms stick together to build everything we see. But in the mirror universe, those rules flip. Antiprotons with their negative charge would orbit positrons, their positively charged counterparts, creating anti-atoms, anti-stars, even anti-galaxies. The symmetry is elegant. For every particle here, there's an opposite there, preserving the balance the Big Bang originally intended. This idea isn't just philosophical. It solves one of cosmology's biggest headaches: why the universe didn't annihilate itself instantly. If antimatter had stuck around in our realm, it would have collided with matter, unleashing titanic bursts of gamma rays and leaving the cosmos empty. But if it slipped into a parallel dimension at the dawn of time, the two could coexist without destruction. It's like having two neighboring cities with identical populations, one filled with people, the other with perfect photographic negatives of them. They never meet, so they never cancel each other out. The evidence for this hidden antimatter realm might already be in our hands. When scientists study cosmic rays, high-energy particles raining down from space, they occasionally detect antihelium nuclei, rare but real. These could be messengers from the mirror universe, tiny fragments leaking through cosmic cracks. Even more compelling are experiments with neutral particles like neutrons, which can oscillate between matter and antimatter states. If these particles flicker between universes, it would explain why antimatter seems so elusive. It's not missing. It's just hiding in plain sight on the other side of reality's curtain. But here's the twist: if the mirror universe is made of antimatter, why doesn't its gravity collapse ours? The answer might lie in the very nature of antimatter. While it carries opposite charge, its gravitational pull appears identical to ordinary matter, meaning antimatter galaxies would tug on ours just like invisible dark matter does. This could solve two mysteries at once: the missing antimatter and the invisible glue holding galaxies together. The implications are staggering. Civilizations could have risen in that antimatter realm, their scientists just as baffled by the absence of matter as we are by antimatter. Supernovas might blaze there with the same brilliance, planets could harbor life, and black holes could warp space-time identically, all while remaining forever out of reach. The universe, it seems, isn't unbalanced after all. It's just been split down the middle, with each half holding up its end of the cosmic bargain. Now the hunt is on to prove it. Particle colliders are searching for anomalies in antimatter behavior, tiny deviations from symmetry that could hint at a mirror world's influence. Astronomers, too, are scanning deep space for gravitational echoes, subtle distortions that might reveal antimatter galaxies tugging at ours from behind the veil. If they succeed, it won't just rewrite the story of the Big Bang, it'll prove that reality is far richer and far stranger than we ever dared imagine. Black holes have always been cosmic enigmas, regions of space where gravity becomes so intense that not even light can escape. But what if these monstrous voids aren't just one-way traps? What if they're secret passageways connecting our universe to its mirrored twin? The math behind this idea is as fascinating as it is mind-bending. According to Einstein's theory of general relativity, black holes don't just bend space-time, they twist it into a funnel so extreme that the fabric of reality might literally tear, creating a bridge to another realm. Imagine tossing a pebble into a still pond. The ripples spread outward, but if you could reverse time, they'd converge back to the point of impact. Now, picture a black hole as that point, except instead of water, it's space-time itself collapsing inward. Some theories suggest that this collapse doesn't end in a singularity, but opens a tunnel, a wormhole, linking our universe to its mirror counterpart. Matter swallowed by a black hole here might not vanish forever. It could re-emerge over there like a cosmic subway shuttling particles between parallel worlds. This isn't just wild speculation. The equations describing black holes often spit out solutions with two exits, one in our universe, one in the mirror realm. Even the event horizon, that infamous point of no return, might not be the end we think it is. Instead, it could be a threshold, a cosmic customs checkpoint where matter gets stamped and sent to the other side. The catch: anything passing through would be utterly transformed, stretched and scrambled by tidal forces until it's unrecognizable. A star falling in here might drizzle out as a stream of energy there, like cosmic spaghetti reconstituted into soup. The implications are staggering. If black holes truly are portals, they could solve one of the biggest paradoxes in physics, the information paradox. Quantum mechanics insists that information can never be destroyed, yet black holes seem to erase it. But if that data isn't lost, just transferred to the mirror universe, the paradox vanishes. It's like burning a book in our world but finding its ashes perfectly preserved in another. Suddenly, black holes aren't destroyers, they're librarians, cataloging reality's secrets across dimensions. But how could we ever prove it? The answer might lie in the echoes of dying stars. When black holes merge, they unleash gravitational waves, ripples in space-time detectable here on Earth. If these waves carry subtle anomalies, extra frequencies, or unexpected patterns, they could hint at matter slipping into the mirror universe. Even stranger, some physicists speculate that mirror matter leaking back through black holes might explain mysterious cosmic rays, particles with energies so high they defy known physics. These could be refugees from the other side, fingerprints of a reality we've yet to fully see. Of course, stepping through a black hole remains firmly in the realm of science fiction for now. The forces near these beasts would shred anything long before it reached the theoretical tunnel, but the mere possibility reshapes how we view the cosmos. If black holes are gateways, then the universe isn't just expanding, it's conversing, whispering to its twin through gravity's silent language. And every time a star vanishes into the dark, it might not be gone. It could just be starting a new chapter, one written in the mirror universe's inverted script. The cosmic microwave background is like the universe's baby picture, a snapshot of its earliest moments, frozen in time and stretched across the entire sky. This faint glow, the remnant heat from the Big Bang, has been studied for decades, revealing the seeds of galaxies and the blueprint of cosmic structure. But hidden within its subtle fluctuations are anomalies that refuse to fit the standard model: oddly cold spots, unexplained alignments, and patterns that seem to whisper of something beyond our universe's edge. What if these cosmic hiccups aren't just statistical noise, but the gravitational fingerprints of a mirror universe tugging at ours from the other side of creation? Take the infamous cold spot, a region of space significantly chillier than its surroundings. Conventional explanations, cosmic voids, or instrumental errors fall short. But if another universe gravitationally interacted with ours in those first fleeting moments, the energy drained away by that invisible pull could leave just such a cold imprint. It's like pressing a finger against a foggy mirror. The distortion reveals a presence you can't directly see. Similarly, certain large-scale patterns in the CMB's polarization, the way its light waves align, seem too perfectly coordinated across vast distances. Could this coherence stem from an external influence, a parallel cosmos imprinting its structure onto ours at birth? The math behind this is breathtaking. When physicists model the early universe's expansion, they find that quantum fluctuations, tiny ripples in space-time, should create a predictable spectrum of hot and cold spots in the CMB. Yet some fluctuations appear smoother or clumpier than expected, as if an unseen hand smudged the cosmic canvas, a mirror universe brushing against ours during inflation. The rapid expansion just after the Big Bang could have warped those fluctuations like a second painter adding strokes to a shared masterpiece. Even more compelling are the hints of asymmetry in the CMB's large-scale structure. The universe's northern and southern hemispheres show slight but statistically significant differences in their distribution of matter, almost as if one side bears the gravitational signature of another reality leaning into ours. Detecting these signals isn't just about spotting oddities, it's about decoding a cosmic language. Scientists are now developing algorithms to sift through CMB data for specific patterns, concentric rings of temperature variation that might indicate a collision with another universe's bubble, or twisted polarization patterns resembling the wake left by a passing gravitational giant. Future telescopes like the upcoming LightBird mission will map the CMB's polarization with unprecedented precision, hunting for these telltale signs. But the most tantalizing clue might lie in the CMB's missing power: certain large-scale fluctuations that appear suspiciously muted. If a mirror universe exerted gravity on ours during inflation, it could have suppressed these fluctuations like a hand damping a vibrating drumhead. The absence of expected energy might actually be the presence of something far more extraordinary, a shadow cosmos, forever entwined with our own, leaving its mark in the quietest echoes of the Big Bang. Finding proof wouldn't just confirm a mirror universe, it would redefine our understanding of reality's architecture. The cosmic microwave background, once seen as a relic of our solitary origins, could become the Rosetta Stone of a multiverse, revealing that we've always been part of a grander, mirrored existence. Every anomaly, every unexplained pattern might be a message from our cosmic twin, a whisper across the eons saying, "We were here too." Time isn't the steady, unchanging river we perceive. It's more like a cosmic elastic band, stretching and compressing depending on where you are and how fast you're moving. Einstein taught us that much with relativity, but what if the mirror universe doesn't just bend time, it flips it entirely? Imagine two clocks side by side, one ticking forward in our world, the other counting backward in its mirrored counterpart. The seconds sync in perfect opposition, like dancers moving in reverse. This isn't science fiction. It's a serious possibility hidden in the math of CPT symmetry, where time's arrow might point the other way across the cosmic divide. Think about black holes, regions where gravity warps time so severely that near the event horizon, minutes for you could be centuries elsewhere. Now picture a mirror black hole where that distortion runs in reverse. Matter falling into our speeds toward a frozen future, while in the twin universe it might be clawing its way out of the past. These mirrored distortions could leave detectable imprints. Gravitational waves, the ripples from colliding black holes, might carry subtle asymmetries, anomalies in timing or spin that hint at a universe where cause and effect unfold in reverse. The real smoking gun could lie in the decay of particles. Take radioactive isotopes which break down at predictable rates in our universe. If scientists ever found atoms that seem to undecay, their particles reassembling over time, it might signal a quantum link to a mirror universe where those processes run backward. Even more tantalizing are neutrinos, those ghostly particles that oscillate between flavors as they travel. Some theories suggest their transformations could be influenced by interactions with mirror neutrinos, effectively borrowing or lending time from the other side. But how would we perceive this inverted time flow? From our perspective, the mirror universe's history would unfold like a rewinding tape, supernovas imploding into stars, galaxies condensing into primordial gas. Yet from their viewpoint, we'd be the ones living backward. It's a dizzying thought, two realities sharing the same events but reading them in opposite orders, like a book whose chapters make sense whether you start at the beginning or the end. The hunt for these temporal discrepancies is already underway. Atomic clocks aboard satellites, which already account for Earth's gravity slowing time, could be repurposed to search for anomalies in deep space, places where time's flow seems subtly tugged by invisible forces. Pulsars, the universe's most precise natural clocks, might reveal irregularities in their rhythmic flashes if their light passes through gravitational fields warped by mirror matter. Even quantum entanglement experiments could hold clues. If particles sync instantaneously across distances, could they also sync across time's mirror? This isn't just about solving a physics puzzle. If time flows backward in the mirror universe, it challenges everything we know about causality. Events there might not just follow different rules, they could redefine what before and after even mean. A star's death here might birth a star there, tangled in a loop where beginnings and endings are two sides of the same coin. The fabric of reality, it seems, isn't just woven from space and matter, but from time's dual threads forever mirroring each other in the dark. The multiverse theory paints a picture of infinite realities, each bubbling into existence with its own unique physics, history, and laws, like a cosmic kaleidoscope of possibilities. But the mirror universe concept throws a fascinating curveball into this vision. Instead of countless disconnected worlds, it proposes something far more intimate, a single, perfect counterpart to our own, bound to us not by chance, but by the fundamental symmetries woven into the fabric of reality. Think of it like this: if the multiverse is a vast ocean of unrelated waves, the mirror universe is the tide, locked in an eternal dance with our own, rising as we fall and falling as we rise. This duality isn't just poetic, it's rooted in hard physics. While most multiverse theories rely on cosmic inflation or quantum branching to spawn independent universes, the mirror universe emerges from something deeper: the mathematical elegance of symmetry. Charge, parity, and time, the trio known as CPT, form a sacred rulebook for our universe, suggesting that flipping all three should leave the laws of physics unchanged. But what if that symmetry isn't just a theoretical exercise? What if it's a blueprint for a real physical twin? In this view, the mirror universe isn't one among many. It's the only other reality that must exist to keep the cosmic scales balanced. The implications are profound. While multiverse theories often leave us drowning in infinite possibilities, the mirror universe offers a razor-sharp prediction. If it's out there, it should mirror our universe's structure down to the atomic level, with galaxies, stars, and planets arranged in perfect opposition. No random variations, no alien physics, just a single, synchronized shadow. This precision makes it uniquely testable. Forget hunting for vague statistical anomalies. Scientists can now search for specific fingerprints, like gravitational echoes from mirror galaxies or quantum particles flickering between realms. Yet here's the twist: the mirror universe might not just coexist with ours, it could be entangled with it. While most multiverse scenarios imagine parallel worlds that never interact, quantum mechanics suggests our twin might be spookily connected to us, with particles here instantaneously influencing their counterparts there. This isn't just another universe, it's a cosmic partner, its fate forever tied to ours. So where does that leave the multiverse? Perhaps these ideas aren't rivals, but pieces of a grander puzzle. Imagine a vast cosmic tree, its branches representing infinite inflationary universes, but on one special branch, a mirrored pair of leaves perfectly aligned. The mirror universe wouldn't negate the multiverse. It would enrich it, offering a rare example of order in the chaos. And if we can prove even one mirrored reality exists, it would revolutionize our search for others, turning the hunt for parallel worlds from philosophy into hard science. The stakes couldn't be higher. Confirming a mirror universe wouldn't just add another entry to the multiverse catalog, it would reveal a hidden layer of cosmic architecture, where symmetry isn't just a quirk of math, but the glue holding existence together. Every galaxy in our sky might have a silent twin, every atom a shadow, and every moment in time an inverted echo. The universe, it seems, has always been a conversation, not a monologue. And we're just beginning to listen. Neutrinos are the universe's most elusive escape artists, particles so ghostly they can pass through light years of lead without a single interaction. Billions stream through your body every second, leaving no trace, as if they're barely part of our reality at all. But what if that's exactly the point? What if their refusal to engage isn't a quirk of physics, but a clue that they're not entirely from our universe? Some physicists suspect these shadowy particles might be cosmic commuters, flickering between our world and its mirrored twin, carrying secrets in their quantum silence. The evidence lies in their bizarre behavior. Neutrinos come in three types: electron, muon, and tau, and they constantly morph between these flavors as they travel, a phenomenon called neutrino oscillation. But here's the puzzle: the math predicting these oscillations has never quite matched observations. There's a missing piece, an unexplained gap in the equations. One tantalizing possibility: neutrinos aren't just oscillating between known states, they're briefly tunneling into the mirror universe, borrowing properties from their invisible counterparts before snapping back. It's like watching a magician's coin vanish and reappear, except the trick might involve an entire hidden dimension. This idea isn't as far-fetched as it sounds. Neutrinos are already cosmic misfits. They're the only particles that don't care about electromagnetism or the strong nuclear force, responding only to gravity and the weak force. That makes them uniquely capable of slipping through barriers other particles can't, including, perhaps, the boundary between universes. If mirror matter exists, neutrinos might be the only particles light enough and aloof enough to dance across the divide, acting as cosmic diplomats between realms. The smoking gun could lie in a phenomenon called sterile neutrinos, hypothetical particles, even more elusive than ordinary neutrinos, interacting solely through gravity. Some experiments, like the liquid scintillator neutrino detector, have spotted anomalies suggesting these phantom particles might exist. If sterile neutrinos are real, they could be the bridge to the mirror universe, ordinary neutrinos transitioning into sterile states as they briefly cross over, then back again, leaving behind telltale gaps in detection rates. Imagine what this means for science. Neutrino detectors, massive, hypersensitive instruments buried deep underground or submerged in Antarctic ice, could become interdimensional observatories. Every time a neutrino seems to vanish or gain unexpected energy, it might be whispering about conditions in the mirror realm. Even more astonishing, if mirror neutrinos have slightly different masses, their gravitational tug could subtly alter the path of our neutrinos, like a hidden hand nudging a pendulum. The stakes are cosmic. If neutrinos truly are shuttling between universes, they might carry more than just quantum states. They could transport information. Flares of neutrinos from a supernova in our universe might be mirrored by a corresponding burst in the other, a synchronized cosmic signal, or perhaps the mysterious neutrino flaw. The background noise limiting dark matter searches isn't noise at all, but the faint chatter of mirror neutrinos bleeding through. Right now, experiments like the Deep Underground Neutrino Experiment and Japan's Hyper-Kamiok are pushing detection to unprecedented precision, hunting for these minuscule anomalies. If they find even a hint of mirror interactions, it won't just solve the neutrino puzzle, it'll crack open a portal to another reality, proving that the universe has been sending us messages all along, written in the faintest ink imaginable. The silent, ceaseless dance of ghostly particles. Gravitational waves have revolutionized astronomy, allowing us to hear the universe's most violent events through ripples in space-time. But what if some of these cosmic tremors aren't just echoes from our universe? Hidden within the data from detectors like LIGO and Virgo could be whispers of collisions happening in a parallel reality. Cataclysms from a mirror universe imprinting faint distortions onto our own. The idea isn't as far-fetched as it sounds. If the two universes share a gravitational link, every black hole merger, every neutron star crash over there might send subtle shivers through the fabric of space here, like distant thunder vibrating a window pane. Take the bizarre case of GW 1924. A gravitational wave event detected in 2019. The signal suggested two black holes merging, but their calculated masses defied expectations, too light to form through conventional stellar collapse. Stranger still, the spin axes of these black holes seemed misaligned in ways that challenged standard models. Could this anomaly be a clue? If one of those objects wasn't entirely ours, but a mirror black hole straying close enough to interact gravitationally, it would explain the odd parameters. Like a left-handed glove brushing against a right-handed one in the dark, the collision's signature would carry traces of its alien origin. The key lies in polarization, the way gravitational waves twist and stretch space. In our universe, mergers produce waves with predictable patterns, like concentric circles radiating outward. But a mirror universe collision might imprint a reversed signature, as if space itself were being tugged from the other side. Advanced detectors now analyze these polarizations with exquisite precision, hunting for events where the ripples seem to spiral the wrong way or arrive fractionally out of sync with expected models. Even more telling would be ghost echoes, secondary waves arriving microseconds after the main signal, as if bouncing off an invisible cosmic boundary between realities. The implications are staggering. If gravitational waves can leak between universes, they'd act as cosmic sonar, mapping the hidden contours of the mirror realm. A collision there might appear here as a distortion with no visible source, a gravitational wave without a corresponding flash of light or burst of radiation. Already, astronomers have catalogued several orphan waves that lack electromagnetic counterparts. While some could be mundane, black holes merging in empty regions of space, others might be our first tangible evidence of a parallel cosmos knocking on space-time's door. Future observatories like the space-based LISA mission could elevate this search to new heights. By measuring lower-frequency gravitational waves, they'd catch the deeper rumbles of supermassive black hole mergers, events so colossal their mirror counterparts would leave unmistakable fingerprints. Imagine detecting twin waves from a single cataclysm, one set from our universe, the other its mirrored reflection, slightly offset in time and polarity. It would be like hearing an earthquake's echo from another dimension. Of course, skeptics argue these anomalies could stem from mundane sources, instrumental noise, statistical flukes, or gaps in our understanding of black hole formation. But that's what makes the hunt so thrilling. Every unexplained wiggle in the data isn't just a mystery, it's a potential doorway. And if we ever catch a gravitational wave that unmistakably carries the mark of the mirror universe, it won't just confirm a theory. It'll prove that when black holes dance, their shadows might be waltzing in another reality entirely. String theory has long been the wild frontier of theoretical physics, a realm where the universe isn't just made of particles, but of tiny, vibrating strings humming through 11 dimensions. It's a framework so vast it could encompass all possible realities, including our mirror universe. Picture our cosmos not as an isolated bubble, but as a membrane or brain floating in a higher dimensional space, like a sheet of paper suspended in a vast, unseen ocean. Now imagine another brain perfectly parallel to ours, separated by a gap so small it's measured in quantum scales, yet so profound it might as well be another reality. This is where the mirror universe could be hiding, not in some distant corner of space, but right next door, separated by dimensions we can't perceive. The beauty of this idea lies in its explanatory power. Dark energy, the mysterious force accelerating the universe's expansion, has baffled scientists for decades. But if our brain and its mirror twin occasionally interact, their gravitational push and pull could manifest as dark energy's relentless push. It's like two magnets repelling each other through a table. We feel the force but can't see the source. Even more tantalizing, these brain collisions might not be rare. Some models suggest they could happen cyclically, triggering new big bangs and resetting the cosmic clock. Our universe's birth might have been just one ripple in an endless dance of colliding realities. String theory's math offers a startling possibility. The mirror universe could be literally inverted, not just in matter and time, but in its very dimensional structure. While our familiar 3 dimensions of space unfurl like a grid, the mirror brain's dimensions might be coiled or twisted, explaining why its particles behave differently. This could answer why dark matter seems to ignore light. It's not that it's invisible, but that it vibrates along strings anchored in the mirror brain, forever just out of phase with our own. The most radical implication, these brains might not be entirely separate. String theory allows for open strings, those within points tethered to a brain, and closed strings which can loop between brains like threads stitching fabric together. If closed strings exist, they could carry forces like gravity across the divide, allowing the mirror universe to tug on ours without ever being seen. That would mean every galaxy in our sky has a hidden twin, its gravity felt but its light forever trapped on the other side. Testing this isn't just a pipe dream. The Large Hadron Collider, while designed to smash particles, might also create microscopic black holes, brief portals where energy leaks between brains. No such leaks have been found yet, but the search continues. Meanwhile, astronomers are scouring the cosmic microwave background for imprints patterns that could reveal ancient brain collisions, like fingerprints left on glass. Even gravitational wave detectors, tuned to the universe's faintest tremors, might catch echoes of mirror black holes merging in a realm we can't see. If string theory is right, the mirror universe isn't just a philosophical curiosity, it's a mathematical inevitability woven into the fabric of reality at the most fundamental level. Every vibration of every string, every fold in the dimensional landscape could be whispering the same truth. We're not alone in the cosmos. We're part of a duality, a cosmic symmetry so deep it resonates across dimensions, waiting for us to listen. The Fermi Paradox has haunted scientists for decades. If the universe is so vast and ancient, where is everybody? Countless galaxies, trillions of stars, yet not a single definitive sign of intelligent life. We've scanned the skies for radio signals, searched for megastructures, even studied distant atmospheres for biosignatures, but the silence is deafening. Unless, of course, we've been looking in the wrong reality entirely. What if the answer to the paradox isn't in our universe, but in its mirrored twin? Consider this: if life arose in the mirror universe under identical physical laws, just flipped in charge, parity, and time, it would face the same cosmic opportunities we did. Planets would form around stable stars, chemistry would give rise to complex molecules, and evolution might sculpt intelligence. But here's the catch: their very existence would be nearly invisible to us. Mirror photons wouldn't interact with our eyes or telescopes. Their radio signals would sail through our detectors unnoticed. Even their planets, if aligned with ours, would cast no shadows in our sky. They could have sprawling civilizations, bustling cities, even interstellar empires, and we'd never know. This idea flips the Fermi paradox on its head. The Great Silence isn't proof we're alone. It's a clue that we're only seeing half the picture. Advanced mirror civilizations might gaze at our universe with the same frustration, wondering why their skies appear empty while the math screams that life should be everywhere. Both realities blind to each other, trapped in a cosmic game of hide and seek. But what if some interactions are possible? Neutrinos, those ghostly particles that barely acknowledge matter, could be the key. If mirror life harnessed neutrino-based communication, their messages might be flooding through us right now, undetected. Or perhaps they've engineered ways to tug on our universe gravitationally, leaving subtle anomalies in galaxy rotations or gravitational waves. Breadcrumbs we're only now learning to decode. The most chilling possibility: they already know we're here. If mirror physicists cracked quantum entanglement secrets, they might use it to probe our universe silently, studying us like shadows on a cave wall. Their probes could be all around us, made of mirror matter, invisible and intangible, a galactic zoo we don't realize we're in. Yet there's hope. As our tools grow sharper, we're learning to hunt for the impossible. Next-generation neutrino detectors might catch patterns that whisper of artificial origin. Gravitational wave observatories could spot the fingerprints of mirror technology warping space-time. Even the strange behavior of dark matter, its perplexing clumpiness, might one day reveal the handiwork of a civilization we've yet to imagine. The Fermi Paradox taught us to question our place in the cosmos. But the mirror universe suggests an even humbler lesson. The universe isn't just bigger than we imagined. It's stranger, more layered, and far more cunning in hiding its secrets. The answer to "Are we alone?" might not be yes or no, but something far more thrilling. We're not alone, we're just looking in the wrong mirror. Simulated universes have long been a mind-bending possibility. What if our reality is nothing more than an advanced civilization's quantum computer humming away in some higher dimension? But here's a twist that cranks the weirdness to 11. If we're living in a simulation, could the mirror universe be its failsafe, a parallel instance running alongside ours like a cosmic backup file? Imagine a programmer testing different variables in identical virtual worlds. tweaking gravity here, adjusting dark energy there, observing how each version unfolds. Suddenly, the mirror universe isn't just a physics curiosity, it's the control group in a grand cosmic experiment. This idea isn't just sci-fi speculation. In computer science, redundancy is key. Critical systems often run mirrored servers to prevent catastrophic crashes. Apply that logic to reality, and our universe might be one of two synchronized simulations, each a slight variation of the other. Maybe the mirror universe is where the programmers rolled back time to fix a bug, or where they dialed up the strength of the nuclear force to see how stars would evolve differently. The anomalies we spot, those unexplained gravitational waves, the neutrino oscillations that defy prediction, could be glitches in the code, artifacts of the simulation's dual instances subtly bleeding into one another. Now, the existential kicker. If we're simulated, how would we ever know which universe is the original? From our perspective, the mirror realm seems inverted, its time flowing backward, its particles flipped. But from their viewpoint, we're the ones who look strange. It's like two characters in a video game, each convinced they're the player, unaware they're both avatars in someone else's experiment. The very fabric of reality might hold clues. Physicists have proposed that if our universe is a simulation, there'd be fundamental limits to how finely space and time can be divided, a pixelation lurking at the smallest scales. Hunt for those telltale signs in both universes, and you might spot which one's running on the higher resolution hardware. The implications spiral outward. If the mirror universe is a backup, could it be older than ours? A prototype where the simulation's architects worked out the kinks before launching our version. Or perhaps it's the opposite, a newer iteration, optimized after observing our universe's flaws. Some theorists even speculate that black holes could be data transfer points, funneling information between the two simulations like cosmic USB ports. Every time a star vanishes into one, its data might be getting uploaded to the mirror realm for analysis. Here's where it gets truly meta. If we're simulated, our creators might be simulated too, nested in an infinite regression of realities. The mirror universe could be their way of stress testing the system, ensuring their own existence doesn't crash. It's a hall of mirrors stretching eternally, with no way to know which reflection, if any, holds the original. The only certainty, whether we're code or consciousness, the mirror universe isn't just our twin. It's our most tantalizing clue that reality is far stranger and far more layered than we ever dared dream. Quantum computers don't just crunch numbers, they dance on the edge of reality itself, leveraging the bizarre rules of quantum mechanics to perform calculations that would take conventional machines millennia. But what if their power extends beyond our universe? The same quantum weirdness that lets qubits exist in multiple states at once might also tether them to their mirrored counterparts in another reality. Think of it like a radio tuned to two stations simultaneously, our universe broadcasting on one frequency, the mirror universe whispering on another. If quantum entanglement truly bridges these realms, then every time a qubit flips, its twin in the mirrored world might flip too, invisible but inextricably linked. This isn't just theoretical sleight of hand. Entanglement has already been shown to defy classical intuition, particles influencing each other instantaneously across vast distances, as if space and time don't apply. Now extrapolate that to the mirror universe. A quantum computer manipulating entangled qubits here could unknowingly be performing a duet with its mirror twin, the two machines operating in perfect, silent sync. The implications are staggering. A calculation performed in our world might ripple into the other, leaving faint traces in the quantum noise, anomalies that could be the first hard evidence of a mirrored reality. Here's where it gets even wilder. Quantum supremacy, the point where quantum computers outperform classical ones, might depend on this very connection. If mirror qubits are subtly influencing ours, they could be providing hidden computational resources, like a shadow processor working in tandem with our own. This could explain why some quantum algorithms solve problems faster than expected. They're not just tapping into our universe's potential, but borrowing power from the other side. But how would we even detect such an interaction? The answer lies in error rates. Quantum computers are notoriously fragile, their qubits prone to decoherence, falling out of sync due to environmental interference. Yet some errors might not be random. If scientists notice patterns in these glitches that align with predictions of mirror-matter interactions, it could be a smoking gun. Imagine a qubit flipping spontaneously, not because of noise, but because its entangled twin in the mirror universe was measured or altered, the most tantalizing possibility. Deliberate communication. If we could engineer qubits to entangle across the cosmic divide, we might send encoded messages, not through space but through the quantum fabric itself. A binary signal here could manifest as a corresponding fluctuation there, like Morse code tapped on the barrier between worlds. It wouldn't require faster-than-light travel or wormholes, just a precise understanding of how quantum threads weave through the multiverse. Of course, skeptics argue this is speculative at best, but consider this: quantum mechanics has repeatedly defied expectation, revealing a universe far stranger than we imagined. If history's taught us anything, it's that the boundaries of reality are never as solid as they seem. Every breakthrough, from relativity to entanglement, started as a wild guess before becoming fundamental truth. Right now, labs worldwide are racing to build larger, more stable quantum computers. With each advance, we're not just pushing the limits of technology. We might be probing the edges of existence itself, running experiments that echo in a universe we've yet to see. And if we ever crack the code, the discovery wouldn't just revolutionize computing. It would redefine what it means to exist in a cosmos that's always been twice as vast as we thought. Dark energy is the universe's greatest unsolved mystery, an invisible force stretching space itself faster and faster, as if reality is being pulled apart by unseen hands. For decades, scientists have struggled to explain its origin. Is it some inherent property of the vacuum of space? A new fundamental force, or could the answer lie not in our universe at all, but in the gravitational tug of its hidden twin? The mirror universe theory offers a radical possibility. What we call dark energy might actually be the cosmic shadow of our counterpart expanding alongside us, its gravity subtly yanking on the fabric of our reality like a hidden conveyor belt dragging ours forward. Picture two soap bubbles floating side by side, their surfaces nearly touching. As one bubble grows, its gentle push distorts the shape of the other, warping its expansion. Now replace those bubbles with universes our own and its mirror twin separated by a thin, higher dimensional gap. If the mirror universe is expanding at a slightly different rate, its gravitational influence could manifest in ours as the relentless push we've labeled dark energy. It's not that space itself is mysteriously accelerating, it's that we're feeling the echo of another reality's growth, a cosmic harmony playing just out of earshot. The math behind this is astonishingly elegant. Einstein's equations allow for gravitational effects to bleed between branes, theoretical membranes that could house parallel universes in string theory. If our universe is a brane hovering near its mirror counterpart, their mutual gravitational attraction would create an effective repulsive force, mimicking dark energy's observed behavior. Even more compelling, this model naturally explains why dark energy's strength is so bafflingly small, a fraction of what quantum field theory predicts. The mirror universe's gravity would dilute across dimensions, arriving in our world as a faint but persistent nudge, exactly matching the subtle acceleration we detect. Clues are already hiding in plain sight. The Hubble constant, the rate of the universe's expansion, has stubbornly refused to settle into a single value, with different measurement methods disagreeing by small but significant margins. Could this tension be a fingerprint of the mirror universe's influence, its expansion rate subtly skewing our own? Even the large-scale structure of the cosmos, the way galaxies cluster in vast filaments and voids, might bear the imprint of mirror matter's gravitational scaffolding, invisible but sculpting the visible universe from behind the scenes. The implications rewrite cosmology's playbook. If dark energy is really the mirror universe's gravity, its acceleration isn't permanent. One day, as the two brains drift apart or collide, the expansion could slow, halt, or even reverse. The fate of the cosmos wouldn't hinge on some abstract cosmological constant, but on the dance of two realities locked in an eternal embrace. It's a revelation that unites two of physics' deepest puzzles, dark energy and the mirror universe, into a single, breathtaking solution. Experiments are already chasing this possibility. Precision measurements of the cosmic microwave background could reveal telltale asymmetries, subtle warping from the mirror universe's gravitational field. Future gravitational wave observatories might detect anomalous ripples, disturbances with no source in our universe, hinting at cataclysms happening just beyond the veil. Even particle colliders could uncover evidence if extra-dimensional gravity slightly alters the behavior of high-energy particles. The hunt for dark energy's true nature has always been a search for the invisible. But what if we've been looking in the wrong direction? The force driving the universe apart might not be lurking in the shadows of our own reality. It could be the whisper of another cosmos, expanding in perfect sync, its gravity reaching across the divide to shape our destiny. If true, the mirror universe isn't just our twin. It's the silent architect of everything we see. The anthropic principle has long been a guiding star in cosmology, the idea that our universe's fundamental constants are perfectly tuned to allow life to exist. Tweak the strength of gravity just slightly, or adjust the charge of an electron, and stars wouldn't shine, atoms wouldn't bond, and life as we know it would be impossible. But here's the twist. What if this delicate balance isn't just a happy accident of our universe, but the result of a cosmic partnership? Enter the mirror universe, not just a theoretical curiosity, but the missing counterweight that keeps reality stable enough for us to be here at all. Think of it like a high-wire act. A lone performer might wobble uncontrollably, but add a balancing pole, and suddenly every movement is stabilized. In this case, the pole is the mirror universe, a realm where every force, every particle, every law of physics is perfectly inverted to counterbalance our own. The strong nuclear force binding atoms here might be slightly offset by its counterpart there, neutralizing tiny asymmetries that would otherwise make matter unstable. Even the vacuum energy of space, the so-called cosmological constant, could be held in check by its mirror twin, preventing runaway expansion or collapse. Without this duality, the universe might have torn itself apart or collapsed into nothingness before the first stars ever formed. This isn't just philosophical hand-waving. The math behind particle physics reveals something startling. Many of the equations describing our universe only achieve perfect symmetry when paired with their mirror counterparts. Take the mystery of neutrino masses, why these ghostly particles are so impossibly light. Some theories suggest their weight is shared with mirror neutrinos, each universe borrowing stability from the other like cosmic conjoined twins. Even the hierarchy problem, the puzzling weakness of gravity compared to other forces, might resolve if gravity's strength is diluted across both realms. its pull split between two realities. But the most profound implication is this: life might not be possible in a solo universe. The mirror realm could be the universe's failsafe, a hidden redundancy ensuring that even if one side veers toward chaos, the other pulls it back. Imagine a pair of dancers, each correcting the other's missteps mid-twirl. Our existence could depend on that silent, eternal coordination. So the next time you marvel at the universe's improbable perfection, remember, we might not be witnessing a solo performance, but a duet. And if the mirror universe is the reason we're here to ponder it at all, then the greatest cosmic joke might be that we've never been alone. We've just been the quieter half of a conversation written into the fabric of reality itself. Cosmic inflation is often described as the universe's first and most dramatic growth spurt, a fraction of a second after the Big Bang, when space itself expanded faster than light, stretching a speck smaller than an atom into a cosmos vast enough to birth galaxies. But what if this explosive moment didn't just create our universe? What if it cleaved reality in two, like a cell dividing, spawning twin realities that expanded back to back, one becoming the world we know, the other its perfect mirrored counterpart? The math behind inflation is stunningly precise, predicting the cosmic microwave background's patterns with eerie accuracy. Yet there's a twist: some equations suggest inflation couldn't have stopped uniformly everywhere. Like a sheet of ice cracking under pressure, space-time might have fractured into distinct phases, each bubble of inflation freezing into its own universe with slightly different properties. Now imagine one of those bubbles didn't just differ in some minor way. It inverted entirely, flipping charge parity and time like a cosmic coin landing on its opposite face. The result: two universes born from the same cataclysm, expanding in tandem but forever separated by an unbridgeable symmetry. This idea transforms the mirror universe from a speculative oddity into a necessary consequence of cosmic inflation. Without it, our universe might be unbalanced, like a spinning top missing half its weight, destined to wobble into chaos. Inflation's equations hint that perfect symmetry isn't just elegant, it's required for stability. Just as every action has an equal and opposite reaction in physics, the mirror universe could be inflation's way of keeping the cosmic books balanced, ensuring the total energy of the multiverse remains zero. One universe's matter is the other's antimatter, one's forward time, the other's reverse, a grand cosmic ledger where every entry has its counterpart. Evidence might already be hiding in the relic radiation bathing our sky. The cosmic microwave background contains mysterious, anomalous voids, regions of space far colder and emptier than inflation alone can explain. If these are bruises left by collisions with the mirror universe's inflationary bubble in those first chaotic moments, they'd appear as subtle temperature dips in the CMB, like fingerprints smudged on a window between worlds. Even the universe's puzzling large-scale asymmetry, one hemisphere slightly denser than the other, could be the gravitational shadow of our twins' expansion tugging at the fabric of shared space-time. But here's the mind-bending part. If the mirror universe was born from the same inflationary field, its physical laws might be identical to ours, not just similar, but mathematically locked in opposition. Every star, every black hole, every strand of DNA here could have its inverted twin there, not by chance but because inflation spun them from the same fundamental thread. It's a vision of reality where the mirror universe isn't just out there, it's woven into the very mechanism that birthed us, a cosmic safeguard written into the universe's DNA. Future experiments could turn this theory from poetry into physics. Next-generation telescopes like the Simons Observatory will map the CMB's polarization with unprecedented precision, hunting for swirls and twists that betray contact with another inflationary bubble. Meanwhile, tabletop quantum experiments might detect minuscule fluctuations in fundamental constants, tiny drifts in the strength of gravity or the mass of electrons, that hint at the mirror universe's gravitational whispers bleeding through. If they find even a hint of evidence, it won't just redefine the mirror universe's origin. It'll prove that inflation wasn't a solitary event. It was the universe's first act of symmetry, a fleeting moment when reality split into perfect halves, each destined to evolve in isolation yet forever bound by the same explosive birth. The mirror universe wouldn't be our twin. It would be our shadow, our counterweight, the silent answer to a question we didn't even know to ask. Why does anything exist at all? Time crystals sound like something ripped from a physicist's wildest dreams, structures that pulse and reset in an endless loop, not through space, but through time itself. Unlike ordinary crystals where atoms arrange in repeating spatial patterns, time crystals break the most fundamental rule of equilibrium. They never settle into stillness, cycling through their states perpetually without energy input, as if rewinding and replaying a cosmic film. But what if this impossible behavior isn't just a quirk of quantum mechanics? What if time crystals are glitches in the fabric of reality, tangible evidence of the mirror universe tugging at our own? The key lies in their symmetry. Just as a snowflake structure repeats when rotated, time crystals repeat at fixed intervals, like a pendulum swinging without friction. But here's the twist: their rhythm isn't driven by forces within our universe. Some theorists propose these oscillations could be synchronized with a mirrored counterpart, their beats echoing across the divide. Picture two metronomes placed back to back, ticking in perfect opposition, one's forward motion fueling the other's reverse. If time crystals in our world are entangled with their twins in the mirror universe, their perpetual motion might not be internal at all, but a cosmic pas de deux, each universe nudging the other to keep the dance alive. This idea isn't as far-fetched as it seems. In labs, time crystals have been created using chains of ions or diamond defects, their eerie stability defying classical thermodynamics. Yet no matter how carefully scientists isolate them, tiny, unexplained fluctuations persist as if an external force subtly resets their cycles. Could these anomalies be whispers from the mirror realm? If particles there interact with ours through higher dimensions or quantum bridges, time crystals would be the perfect receptors, their rhythmic structure acting like a tuning fork resonating with vibrations from the other side. The implications are staggering. If time crystals are indeed cosmic antennas, they could be our first functional link to the mirror universe. Manipulating their oscillations might allow us to send or detect signals across the divide, not through space, but through time's mirrored flow. Imagine encoding data in a time crystal's pulses, only for it to reappear in the mirror universe as a reversed sequence, like a message written in invisible ink that only becomes legible when held up to a parallel light. Even more tantalizing, time crystals might explain why the arrow of time feels so absolute in our universe, yet so reversible in quantum equations. If their behavior is dictated by a mirrored counterpart where time flows backward, their unbreakable rhythm could be the universe's way of harmonizing two opposing temporal streams. It's as if reality itself is a vinyl record, with one side playing forward and the other backward, the needle of existence gliding effortlessly between them. The hunt for proof is already underway. Researchers are probing time crystals for anomalies, unexplained phase shifts, or energy fluctuations that betray external influence. Others are simulating mirror matter interactions in quantum computers, watching for telltale syncopations in virtual time crystals. If they find even a hint of cross-universe coupling, it wouldn't just validate time crystals as a new state of matter. It would crack open a portal to the mirror universe, proving that the boundaries between realities aren't walls, they're rhythms waiting to be decoded. The holographic principle turns everything we think we know about reality inside out, literally. Imagine the universe isn't a vast three-dimensional expanse but a shimmering illusion, like a movie projected onto a cosmic screen. According to this radical idea, all the information that makes up our reality, every star, every atom, even your own thoughts, is encoded on a two-dimensional surface at the very edge of space-time. It's as if the universe we experience is just a hologram, a three-dimensional echo of data etched onto a distant, flat boundary. But here's where the mirror universe comes crashing into the picture. If our reality is a projection, what's stopping there from being another image flickering on the reverse side of that same cosmic film? Think of it like a vinyl record. The grooves on one side encode a symphony, our universe, with its galaxies and gravity. Flip it over, and the grooves on the opposite side play a mirrored version of the same composition, identical yet inverted. The holographic principle suggests the mirror universe might be exactly that, the flip side of reality's record, a second projection emanating from the same two-dimensional source. This isn't just poetic symmetry, it's a mathematical inevitability in some models of quantum gravity. The surface encoding our universe's data wouldn't just generate one hologram, it could generate two, back to back, like a projector casting light in opposite directions. The implications are staggering. If the mirror universe is the hologram's other side, then every event here is inextricably linked to events there. A black hole swallowing matter in our world might ripple through the 2D boundary and manifest as a white hole spewing energy into the mirror realm. Even quantum entanglement, the spooky connection between particles, could be a side effect of this deeper holographic duality, with entangled pairs simply being projections of a single, unified thread on the 2D surface. Evidence for this wild idea might already be hiding in plain sight. The holographic principle predicts that space-time should have a subtle pixelation, a minimum unit of distance beyond which the concept of smoothness breaks down. Incredibly, experiments with ultra-high-energy particles suggest space might indeed have a granular structure, like a digital image revealing its pixels when zoomed in too far. If this pixelation aligns with holographic predictions, it could mean we're not just living in a hologram, we're sharing the projector with another universe entirely. But the most mind-bending twist, the holographic mirror universe wouldn't just be a separate reality, it would be part of the same fundamental object as ours, like two shadows cast by a single flame. Any change to the 2D code would alter both projections simultaneously, meaning the mirror universe isn't just our twin. It's our inverse, our complement, the yin to our yang, written into the fabric of existence itself. Future experiments could turn this speculation into science. Gravitational wave detectors might catch anomalies, ripples in space-time that seem to arrive from no source in our universe, but match predictions for holographic echoes from the mirror side. Quantum computers manipulating information at the most fundamental level could inadvertently brush against the 2D boundary, revealing glitches that betray the hologram seams. If the holographic principle is right, then the mirror universe isn't just out there. It's written into the very code of reality, a parallel projection dancing on the same thin surface as our own. We're not just searching for a cosmic twin, we're decoding the universe's deepest secret, that all this complexity, all this grandeur, might just be a shadow on the wall of something far simpler and far stranger. Quantum decoherence is the silent thief of the quantum world, the process that takes particles from a haze of infinite possibilities and forces them to choose a single, definite state. It's why Schrödinger's cat can't stay both alive and dead forever. and why we never see everyday objects blurring between positions like quantum particles do. But here's the twist. Decoherence doesn't just erase quantum weirdness, it might be shipping it off to another reality entirely. Some physicists argue that when a quantum system collapses, the lost possibilities aren't destroyed. Instead, they slip through the cracks of our universe, emerging in the mirror realm as tangible events. Imagine flipping a quantum coin. In our world, it lands heads, but at the exact same moment, its mirrored counterpart lands tails in the other universe. Every quantum decision here could spawn an equal and opposite outcome there, like cosmic backstage hands ensuring the multiverse's books stay balanced. This isn't just philosophical hand-waving. It's a solution to one of quantum mechanics' biggest headaches, the measurement problem. If decoherence shunts quantum ambiguity into the mirror universe, it explains why we only ever observe definite states in our world. The superposition never truly vanishes, it just relocates, playing out in a parallel reality where the coin did land tails, the cat did survive, or the particle did tunnel left instead of right. The math behind this is startlingly elegant. When particles entangle, linking their fates across space, their combined wave function describes all possible outcomes. Decoherence appears to collapse that wave function from our perspective, but the equations suggest the full picture is preserved in a larger, multi-universe framework. The mirror universe becomes the repository for every road not taken, every quantum possibility our reality discarded. It's like a cosmic recycling bin, but instead of deleted files, it holds deleted futures. Experiments might already be hinting at this crossover. Quantum systems sometimes exhibit tiny, unexplained energy losses during decoherence, as if information is leaking into an invisible sink. Others show odd correlations between seemingly unrelated particles, as if they're being nudged by events in the mirror realm. Even the infamous double-slit experiment, where particles act as both waves and particles, could have a mirror counterpart. The interference patterns we see might be influenced by invisible waves from the other side, like ripples from a parallel pond overlapping with ours. The implications rewrite how we view reality. If every quantum event branches into twin outcomes across universes, then the mirror world isn't just a passive reflection, it's an active participant in shaping our own. Life's unpredictability, from mutations in DNA to the firing of neurons, might trace back to this silent exchange. And if we could somehow peer beyond the veil, we might catch glimpses of roads untraveled histories where dinosaurs never died, where civilizations rose differently, or where you made that left turn instead of a right. The hunt for proof is on. Cutting-edge quantum sensors are now precise enough to detect minuscule energy discrepancies that could betray information slipping between realities. Others are redesigning decoherence experiments to hunt for echoes, subtle patterns in particle behavior that hint at interference from the mirror side. If they succeed, it won't just solve a quantum mystery. It'll prove that the universe has been keeping secrets in plain sight, whispering to its twin through the quiet collapse of a particle's possibilities. Neutron stars are nature's most extreme laboratories, cosmic pressure cookers where matter gets crushed to densities so intense that a single teaspoonful would weigh billions of tons on Earth. These stellar corpses, born from the explosive deaths of massive stars, are so dense they warp the very fabric of space-time around them. But what if their unimaginable gravity is doing something even stranger, acting as a cosmic magnet for matter from another universe? Hidden deep within their cores, neutron stars might be hoarding mirror matter, the elusive substance of our universe's twin, and the key to unlocking one of cosmology's greatest mysteries. Picture a neutron star's interior as a quantum soup, where atomic nuclei dissolve into a sea of neutrons packed shoulder to shoulder. Under these extreme conditions, the boundary between ordinary matter and something far weirder begins to blur. If mirror particles exist, their unique properties immune to electromagnetic forces but still bound by gravity, would make them perfect candidates to sink straight to the star's core, like heavy sediment settling at the bottom of a lake. Over millennia, mirror neutrons, mirror protons, and even entire mirror atoms could accumulate, forming a hidden layer beneath the star's crust. This wouldn't just be a sprinkling of exotic particles, it could be a substantial fraction of the star's mass lurking undetected. The presence of mirror matter would leave subtle but measurable fingerprints. Neutron stars spin, some rotating hundreds of times per second, and their precise rotation rates are tracked with incredible accuracy by radio telescopes. If mirror matter clusters asymmetrically in the core, it could create tiny imbalances in the star's gravitational field, causing slight wobbles or glitches in its spin anomalies that defy standard astrophysical models. Even more telling would be the star's cooling rate. Neutron stars are born blisteringly hot but gradually radiate heat away. Mirror matter, if it interacts weakly with ordinary matter, could act as an insulator, trapping heat and making certain neutron stars inexplicably warmer than their age would suggest. Perhaps the most tantalizing possibility involves neutron-star collisions. When these ultra-dense objects spiral into each other, they unleash gravitational waves and spectacular kilonova explosions. But if one or both stars harbored mirror matter cores, the collision's aftermath might look fundamentally different. Mirror particles, unable to interact with ordinary light, would carry away energy invisibly, leaving behind discrepancies in the observed brightness or heavy element production. Some theorists even speculate that mirror matter could trigger exotic phases of matter like quark-gluon plasma, sooner than expected during the merger, altering the gravitational wave signal in ways future detectors might spot. The hunt for these clues is already underway. Astronomers are combing through data from neutron-star mergers like GW 1717, searching for mismatches between gravitational wave predictions and actual observations. Others are studying isolated neutron stars, like the enigmatic object at the heart of the Cassiopeia, a supernova remnant, whose surprisingly rapid cooling might hint at a mirror matter heat sink deep inside. Even pulsars, neutron stars that beam radio waves like cosmic lighthouses, could be hiding secrets. If their beams flicker unpredictably, it might not be due to surface quakes, but mirror matter sloshing in their cores, perturbing their magnetic fields. If neutron stars do harbor mirror matter, the implications would stretch far beyond astrophysics. These ultra-dense objects wouldn't just be relics of dead stars, they'd be cosmic archives preserving samples of another reality. Studying them could reveal the mirror universe's particle masses, its nuclear forces, even whether it hosts mirror chemistry or mirror life. A single anomalous neutron star could be the Rosetta Stone that deciphers the hidden half of existence. The universe has always whispered its secrets in extremes: black holes that warp space, quasars that outshine galaxies, and now perhaps neutron stars that straddle realities. As we peel back their layers, we might find more than just the remnants of collapsed stars. We might uncover the first tangible proof that we're not alone in the cosmos, just one half of a grand, mirrored whole. The Boltzmann brain paradox is one of those ideas that starts as a playful thought experiment and quickly spirals into an existential crisis. Imagine if, instead of a vast, ordered cosmos, you were just a lone, self-aware brain floating in the void, randomly assembled by quantum fluctuations. No stars, no planets, just a solitary consciousness hallucinating an entire universe. Statistically, in an infinite expanse of time and space, Such a freak accident should be more likely than the existence of our improbably structured reality. So why aren't we all Boltzmann brains? The answer might lie not in our universe alone, but in its mirrored twin, a cosmic anchor keeping the chaos at bay. Think of the mirror universe as a counterweight in a grand existential balancing act. In isolation, our universe's improbable order seems like a statistical miracle. But pair it with an identical counterpart, and suddenly the scales tip toward stability. Every particle here has its mirrored twin there, every conscious observation tethered to an equal and opposite one across the divide. The randomness that could spawn a Boltzmann brain in a solo universe gets cancelled out like noise reduction in a stereo system, one channel static drowned by the other's symmetry. This isn't just philosophy, it's math. The combined probability of two perfectly ordered universes arising together is exponentially higher than one defying entropy alone. Here's where it gets even wilder. The mirror universe doesn't just stabilize reality, it could explain why we perceive time's arrow at all. Boltzmann brains, unmoored from causality, would experience time as a jumbled mess. But in a mirrored cosmos where entropy flows in opposite directions, our perception of orderly cause and effect might emerge from the interplay between the two. Like two pendulums swinging out of sync, the combined system resists chaos, creating the illusion of a linear timeline. The past feels fixed because the mirror universe's future is pulling it taut, and vice versa. Critics argue this is a Copernican dodge, an elaborate way to avoid the paradox's unsettling implications. But consider the alternatives. Without the mirror universe, we're left with two equally bleak options. Either we are Boltzmann hallucinations and the cosmos is a lie, or our universe's order demands a fantastically unlikely fluke. The mirror solution offers a third path, one where symmetry, not chance, guarantees reality's coherence. It turns a philosophical nightmare into a feature of cosmic design. The echoes of this idea ripple through modern physics. Quantum decoherence, where particles choose definite states, might be the microscopic version of this anchoring effect, our universe's outcomes solidified by their mirror counterparts. Even consciousness itself, that elusive spark of perception, could be a shared phenomenon, flickering between realities like a flame sustained by dual wicks. So the next time you marvel at the universe's improbable order, remember, it might not be a fluke or an illusion, but part of a mirrored pact written into the fabric of existence. The Boltzmann brain paradox doesn't just question reality, it points to its hidden half, a silent partner ensuring the cosmos stays sane. And if that's true, then the greatest proof we're not alone in the universe isn't out there in the stars. It's woven into the very nature of our thoughts. Entropy is the universe's silent timekeeper, the force that makes milk mix into coffee but never unmix, that turns a sandcastle into a shapeless mound but never back into towers. It's why we remember the past but not the future, why broken eggs don't reassemble themselves. But beneath this seemingly one-way street lies a profound mystery. Why does time's arrow point forward at all? The answer might not lie in our universe alone, but in its mirrored twin, where entropy could be running in reverse, creating a cosmic seesaw that keeps reality in perfect balance. Picture two hourglasses placed back to back, one pouring sand downward while the other pours upward. In our universe, entropy increases, systems move from order to disorder. But in the mirror universe, entropy might decrease, with chaos gradually organizing itself into structure. Together, they'd form a closed loop, ensuring the total entropy of the multiverse remains constant. It's a radical twist on thermodynamics, not just a law for our reality, but a partnership between two. This isn't just poetic symmetry, it's embedded in the math. The equations governing entropy don't inherently favor one direction over the other. They only appear to because we're trapped in a single frame of the cosmic film. The mirror universe could be the missing reel playing the same movie in reverse. Think of a deck of cards shuffled into randomness. In our world, that's the inevitable end state, entropy's triumph. But in the mirror universe, that same deck might be unshuffling itself, cards rearranging into perfect order without anyone touching them. From our perspective, this would seem impossible, a violation of thermodynamics. But from the multiverse's vantage point, it's just balance, one universe's chaos offset by the other's emerging order. Even black holes, those ultimate entropy factories, could have mirror counterparts where matter isn't crushed into singularities, but uncrushed into complexity, like a cosmic exhale after our universes inhale. The implications ripple across physics. Why do we only observe time moving forward? Because we're locked into one half of a duality, like seeing only the crests of waves while the troughs exist invisibly beneath. The mirror universe's backward flow could be the anchor that makes our forward flow possible, ensuring causality doesn't spiral into paradox. Quantum events that seem random here, like a particle tunneling through a barrier, might be deterministic when viewed across both realities, with the mirror universe's version of the event completing the equation. This duality could even solve the universe's initial conditions problem. Why did our cosmos start with such astonishingly low entropy, a state so improbably ordered that it's fueled debates for centuries? Because it wasn't the true beginning, just one half of a symmetrical split. The Big Bang's low entropy here might be mirrored by high entropy there, like a diver pushing off the edge of a pool, their motion balanced by the water's equal and opposite reaction. Experiments are already probing this wild idea. Researchers studying quantum systems near absolute zero have observed fleeting moments where entropy appears to decrease locally, tiny reversals that could be echoes of the mirror universe's influence. Others are modeling entangled particles to see if their decoherence patterns hint at a hidden partner universe absorbing lost entropy. Even the search for time-reversed gravitational waves, ripples that arrive before their cosmic source, could reveal a mirror reality where cause and effect are flipped. If this is true, then time's arrow isn't just a feature of our universe. It's a conversation between two realities, a cosmic pact written into the fabric of existence. Every moment of decay here might be matched by a moment of creation there, every shattered glass here mirrored by one reassembling there. The universe, it seems, has always been a dance of duality, and entropy is just the rhythm keeping time. Wormholes have long captured our imagination, cosmic tunnels bending space-time so radically that a journey through one could span light years in an instant. But what if these hypothetical shortcuts don't just bridge distant corners of our universe? What if they're not corridors through space, but doorways to its mirrored counterpart? The math behind wormholes reveals something astonishing. The same equations that allow for these space-time warps also permit them to twist into connections between parallel realities. Picture a wormhole not as a straight subway line tunneling beneath the cosmic city, but as a looking glass, its exit not just elsewhere, but inverted, a place where matter is antimatter, time flows backward, and every physical law we know flips like a reflection in a pond. The idea hinges on the geometry of wormholes themselves. In theory, a traversable wormhole, one stable enough to pass through, requires exotic matter with negative energy to prop open its throat, preventing collapse. But here's the twist. The properties of this exotic matter eerily align with predictions for mirror matter. If negative energy is the gravitational shadow of particles from the mirror universe bleeding into ours, then every stable wormhole might inherently be a bridge between realities. It's as if the universe's plumbing isn't just linking two sinks in the same house, its connecting faucets in parallel dimensions. Consider what this would mean for a traveler daring enough to step through. Crossing the threshold, you wouldn't emerge in another galaxy, but in a realm where your very atoms are inverted. Your electrons would flip to positrons, your quarks to antiquarks, and your biochemistry would unravel like a sweater tugged at a loose thread. Even stranger, your perception of time might reverse. A clock ticking forward in our universe could appear to run backward in the mirror wormhole's exit, like watching a film reel in reverse. The wormhole wouldn't just transport you, it would transform you, rewriting the rules of your existence with every step. The implications for physics are staggering. Wormholes acting as mirrors would resolve one of their biggest paradoxes, the problem of causality. Normally, a wormhole could create time loops, allowing information to circle back and create contradictions like sending a message to your past self. But if the exit lies in a universe where time flows oppositely, the loop snaps. Your future in the mirror realm becomes your past in ours, preserving causality like two gears turning against each other. Suddenly, wormholes aren't just shortcuts, they're cosmic synchronizers, keeping the multiverse's clockwork in harmony. Evidence for this wild idea might already exist in the form of black holes. Some theories suggest that what we perceive as a black hole's singularity could actually be the throat of a wormhole leading to the mirror universe. When matter falls in, it doesn't vanish. It reemerges there like water draining from one sink into another. This could explain why black holes seem to destroy information, a big no-no in quantum physics. It's not destroyed, just relocated. The Hawking radiation they emit might even carry faint imprints of mirror matter, like steam rising from a parallel pot. The search for these mirrored wormholes isn't just theoretical. Gravitational wave observatories could spot anomalies in black hole mergers, echoes, or delayed signals hinting at a hidden tunnel between universes. Even more tantalizing, if mirror matter leaks through wormholes, it might alter the spin of certain black holes in ways telescopes could detect. A black hole spinning the wrong way could be the cosmic signpost we've been waiting for, a flare marking the entrance to the looking glass. But here's the most mind-bending thought of all. If wormholes connect mirrored realities, then every one that forms in our universe must have a twin in the other, a linked pair like quantum entangled particles. This means the mirror universe isn't just out there, it's woven into the fabric of our own, stitched together by a labyrinth of tunnels we're only beginning to imagine. The cosmos isn't just expanding, it's folding, doubling back on itself in ways that make here and there meaningless. Wormholes might not just be bridges or mirrors. They could be the universe's way of whispering to itself across the void. The idea that our universe might be a simulation isn't just sci-fi speculation. It's a serious hypothesis debated by physicists and philosophers alike. Think of reality as an unfathomably advanced computer program, with every star, every atom, even consciousness itself rendered in perfect detail. But if we're living in a simulation, where's the proof? The answer might lie in the tiny cracks, glitches in the code, places where the rules of physics stutter or break, and here's where the mirror universe comes in. What if it's not just a cosmic twin, but a backup instance, a parallel simulation running alongside ours as a failsafe or debug mode? Picture a game developer testing two versions of a virtual world simultaneously, one live, the other a sandbox where they tweak variables and fix bugs. Our universe could be the live build, while the mirror universe is the testing ground. Identical in structure but subtly altered to probe the limits of reality's programming. Any inconsistencies we spot, places where particles behave unpredictably or constants like the speed of light seem to waver, might not be random errors. They could be artifacts of the simulation's dual instances, bleeding into one another like overlapping code. Take the infamous fine structure constant, a number governing the strength of electromagnetic forces. Recent studies suggest it might vary slightly across the cosmos, a cosmic typo that defies explanation. If our universe is a simulation, this inconsistency could be a sign of incomplete debugging, a parameter that wasn't perfectly synced between our reality and its mirrored counterpart. Even more telling are quantum anomalies, particles that tunnel through barriers or entangle across distances faster than light. These unreal behaviors might not be bugs at all, but features of a deeper architecture, hints that the simulation's codebase spans multiple realities. The mirror universe could also explain why some physical laws feel oddly fine-tuned for life. If our simulation's programmers needed a control group to test different configurations, the mirror realm might be running a slightly modified build, one where gravity is stronger or the weak nuclear force weaker. Comparing the two could reveal the source code behind reality's constants, like reverse engineering software by studying its beta versions. But the most chilling possibility: the mirror universe isn't just a backup, it's a quarantine. If our simulation ever crashes or gets corrupted, the system might fail over to its mirrored instance, resetting history with minimal disruption. Those moments when reality feels uncanny or déjà vu strikes could be fleeting glimpses of the switch, like a screen flickering during a server transfer. The hunt for these digital fingerprints is already underway. Particle colliders are probing ever higher energies, searching for deviations from predicted behaviors that might betray the simulation's resolution limits. Astronomers are scanning distant quasars for patterns in their light that could resemble data compression artifacts. Even quantum randomness, long assumed to be truly unpredictable, is being tested for hidden algorithms, the cosmic equivalent of spotting pseudorandom number generation in a video game. If the universe is a simulation, the mirror realm might be our best chance to peek behind the curtain. Every anomaly, every unexplained fluctuation could be a line of code waiting to be deciphered, a message from the programmers hidden in plain sight. And if we ever crack it, the discovery wouldn't just rewrite physics. It would reveal that reality has always been a shared server, humming with more than one instance of existence. What if consciousness isn't confined to brains, but woven into the very fabric of reality? Panpsychism, the radical idea that awareness is a fundamental property of the universe like mass or charge, suggests that everything from atoms to galaxies might possess some rudimentary form of experience. Now take that concept and reflect it across the cosmic divide. If our universe flickers with the faint glow of sentience, could its mirror twin be doing the same, doubling the cosmos's capacity for thought? The implications are staggering, not just for how we see reality, but for what reality might see in us. Picture the universe as a vast neural network, with galaxies acting like neurons firing across the void. Electromagnetic signals, gravitational waves, quantum entanglements, these could be the equivalent of cosmic synapses, transmitting information on scales we can barely fathom. If panpsychism holds, then the mirror universe would be an identical neural twin, its thoughts inverted in charge, parity, and time, yet just as real. Every star here might have a mirrored counterpart there, not just in structure but in some dim, reverberating echo of awareness. This isn't just poetic speculation. Quantum mechanics already hints at a universe deeply interconnected, where particles influence each other instantaneously across vast distances. If consciousness arises from these fundamental interactions, then the mirror universe's particles, entangled with ours since the Big Bang, could be part of the same sprawling mind. A supernova's death throws in our realm might ripple into its twin's consciousness, or a black hole's formation here could trigger a mirrored experience there, like a cosmic déjà vu. But here's the real mind bender. If the mirror universe thinks, does it think backward? With time flowing oppositely, its stream of consciousness would unfold in reverse, its memories our future, its perceptions inverted. Imagine a cosmic dialogue where our universes now is its mirrors then, each completing the other's sentences across the arrow of time. Communication would be impossible, or would it? Quantum entanglement defies classical notions of time and space. If thoughts can entangle too, the two universes might share a silent, timeless conversation, their collective awareness transcending linear causality. The most haunting question isn't whether the mirror universe is conscious, it's whether it knows we're here. If awareness scales with complexity, as some panpsychists argue, then mirror galaxies could harbor civilizations just as introspective as ours, gazing at their skies and wondering why their universe feels half empty. Their scientists might ponder the same anomalies, missing antimatter, dark matter's pull, and arrive at the same staggering conclusion: a mirrored reality, its existence inferred but forever out of reach. Yet evidence might lie closer than we think. Human consciousness itself could be a microcosm of this cosmic duality. Studies of split-brain patients reveal that the mind can fracture into parallel streams of awareness, each half processing reality differently. Could the universe be doing the same, with our experience of self just one hemisphere of a vast mirrored brain? Even mystical traditions speak of unity beyond duality, a hint, perhaps, that the separation between universes is illusory, and consciousness the thread stitching them together. The search for answers won't be easy. How do you detect a universe's thoughts when you're inside its mind? Some researchers propose hunting for anomalies in quantum coherence, places where particles behave as if guided by a larger awareness. Others suggest that the universe's fine-tuning for life isn't just coincidence, but the residue of a self-reflective cosmos, its laws sculpted by the weight of its own contemplation. One thing's certain: if panpsychism is true and the mirror universe shares this boundless awareness, then reality isn't just stranger than we imagined. It's stranger than we can imagine, a place where existence doesn't just happen, but witnesses, where every atom here and its twin there are notes in a cosmic fugue of thought. The universe might not just be alive, it might be awake, and its reflection, it's watching back. The mirror universe theory isn't just a wild idea, it's a symphony of possibilities, harmonizing some of the most baffling notes in modern physics. Think about it: dark matter's ghostly grip on galaxies, the eerie synchrony of entangled particles, even the universe's stubborn preference for matter over antimatter. Each could be a clue pointing to a reality we've yet to fully see. This isn't science fiction. It's science at its most daring, where the equations on our chalkboards might be describing not just one cosmos, but two. For decades, physicists have wrestled with cosmic anomalies that refuse to fit neatly into the standard model. Take dark matter, for example. We've built underground labs, launched space telescopes, and scanned the skies for any trace of this invisible substance, yet it remains elusive. But if dark matter is just ordinary matter from the mirror universe, its invisibility suddenly makes sense. It's not hiding. It's simply operating on a frequency we can't detect, tugging at our galaxies through gravity's silent handshake. The same goes for quantum entanglement's spooky action at a distance. What if particles aren't communicating faster than light? What if they're not communicating at all, just mirroring each other because they're fundamentally linked across the cosmic divide? The implications stretch even further. If the mirror universe exists, it could rewrite our understanding of time itself. Imagine a realm where cause and effect flow backward, where black holes birth stars instead of devouring them, and entropy conspires to create order instead of chaos. This isn't just a fun thought experiment, it's a potential solution to one of physics' greatest puzzles. why time has a direction at all. The arrow we experience might not be absolute, but relative, a local quirk in a multiverse where time's flow is as fluid as a river splitting around a rock. And let's not forget the Fermi Paradox. If life arose in the mirror universe under identical physical laws, their civilizations could be as numerous as ours, yet forever invisible, their light and signals slipping through our hands like smoke. The great silence of the cosmos might not mean we're alone. It might mean we're only hearing half the conversation. But here's the most thrilling part: we're on the verge of testing these ideas. Gravitational wave detectors are listening for echoes of mirror black holes. Quantum computers are probing the edges of reality for glitches that betray another universe's influence. Even the humble neutrino, that cosmic ghost, might be carrying messages from the other side in its oscillations. Every anomaly we uncover, every discrepancy in the data, could be a crack in the mirror, a glimpse into a reality that's been there all along, waiting for us to notice. So what lies beyond the mirror? Perhaps a universe where our history is their future, where our particles are their antiparticles, where every law we hold sacred is inverted yet equally valid. Or maybe something even stranger, a realm that defies all analogy, reshaping not just our science, but our very sense of place in the cosmos. One thing's certain: the journey to find out will be the greatest detective story humanity has ever undertaken. Now it's your turn. Do you think the mirror universe is out there? Could it solve the mysteries that keep physicists up at night? Drop your thoughts in the comments. We're all part of this cosmic conversation. And if you're hungry for more deep dives into the universe's grandest puzzles, hit that subscribe button. The universe, it seems, is just getting started.